speaker is Camilo from University of Paris 1, and he will present us generating constraint programs for variability model reasoning, a DSL and solver-agnostic approach. Welcome.
So good afternoon, everybody. I'm very happy to be here before you. The work we've done today, we're going to present today, has been done in collaboration with Raul, Mazo, and Jacques from two other institutions in France. And before I begin, I wanted to give a little summary that you can keep in the back of your mind throughout the presentation so we can always remember why we're here. So in one single sentence, what this is all about, it's an approach to be able to generate constraint programs for different types of variability modeling languages for very different types of constraint solvers. So you can decouple both. And we're going to see exactly what that means. And if you're not entirely clear on what any of those terms mean, don't worry. We're going to go little by little on what they mean. In terms of the presentation, we're going to look at a little bit at the background on the field and why we're doing this. Then we're going to take a very example-driven approach to see what we're doing concretely. Then we're going to see the prototype and the implementation and the architecture. And finally, we're going to conclude and see a little bit what's next for us. All right. So what's software product line engineering? This field that Sandro mentioned yesterday, and I hope you remember his presentation, but essentially it's an engineering field where we're trying to create families of related products that have connected, overlapping functionalities, and they reuse software assets, either components, requirements, or any other type of element that can be reused between software elements. And the idea is that put together, all of these software systems create what we call a software product line. Now, the key idea is that we're going to systematize reuse. It's a way to make more efficient the reuse of assets to create related systems. Now, one of the unique things about software product line engineering is that there's an artifact called the variability model. And this variability model is going to depict a couple things. First of all, you're going to have features. Then you're going to have this notion of variability among these features. Think how they can be included or not in a given system. And finally, we have some constraints on the presence of these features. Now, what are these features concretely? Well, what they represent in general are sets of requirements that are cohesive from some perspective. Generally, it's from the perspective of the stakeholders, so not necessarily tied down to the code level. It's higher level requirements of a system. And we use these models for three main tasks. One is for configuration, finding out valid collections of features for systems we want to create. We want to be able to generate the code of these systems as much as possible from the reusable assets we have. And finally, in dynamic contexts, we can use the models as a sort of decision model for systems that can reconfigure themselves at runtime. So these are the main three things that we do with these artifacts. And what do they look like? Well, here's a concrete example of one. This is a variability model for an accessible web browser, taken from a publication cited in the bottom. And what you can see here is that the boxes, they represent the features, so the components of the system, if you will, from obviously a user-facing perspective. The relationships between the boxes represent the variability, whether it's mandatory, the inclusion of a certain feature, whether it's optional. And you can also have one-to-many relationships with the little circles. So there you can have multiplicities, as if you were in UML. You could say, I want to have one of the following three features, for example. And so we can also add arbitrary logical constraints that connect any number of features. And that's what you see at the bottom. Even we can think about attributes of features. But for now, this is just an example, and we're going to go slowly look at this more and more in depth. So, automated analysis of these models is quite an important thing. Why is it? Well, fundamentally, these models are going to grow in size quite quickly. If you look at industrial size models, you can see that normally they have more or less several thousand features. In Renault, for example, they use a single car can have about 10,000 features and many numbers of combinations that are valid. You can see it when you try to configure a car on their website. They use internally these tools to give you the allowed configurations. And you need automation. At some point, it's just so big that you can't keep it straight in your mind. But these are software artifacts. And all of us know that anything we do in a computer is probably going to have some mistake somewhere. It's inevitable. So we must check it, we must validate it. But it's not, simple. Fortunately, it turns out that configuring these models and checking them are both conceptually and operationally very similar tasks. And both of them require doing the same thing, which is formalizing the models into some executable representation for reasoning. Much like the previous presentation uses solvers, well, we use something kind of similar, another type of representation. So how is it done in the state of the art? It's been like this for a while now, but it always follows the same idea. You have a variability model in some variability modeling language, which you transform into some formal representation, normally the input for a constraint solver, and from that you do some analysis and you get the results you want. Are there solutions? Is the model void? Are there no solutions? And so on. You will notice that this is quite ad hoc because you're always tied down to a single language and a single solver. You're always doing this to transform something for your needs. But this means it's tool specific. And there's no standards. Nobody agrees on how to do this. This is the state of affairs today. In addition, if we want to add new capabilities and be able to analyze new languages or use new solvers, then we end up having to write new transformations. And this is not ideal. We don't want to repeat ourselves. We don't want to redo pieces of code that we have already done, especially when they're similar. It makes no sense that the field of systematizing reuse is not very good at reusing its own stuff. The other problem is that fundamentally it's been shown that these problems are combinatorial. So it's an NP-complete fundamentally. And that means there's no silver bullet and no solver is perfect for any specific problem instance. And you end up having to fiddle around with the solvers you want to use for every specific case. So our team looked at this and we came up with an idea of trying to simplify in some ways and also add the additional mechanisms to solve these problems and to be able to bring some unity and standardization to the field. So the first thing we're going to do is we're going to take the arrow we just saw, so this transformation, and we're going to split it and we're going to make two steps. So first, we're going to use the same models we already saw, but we're going to add a specification of their semantics. We're going to say how we want to depict the semantics of these models. They will be translated into what we call a pivot intermediate representation. Think of the intermediate code in a compiler before it goes to the back end. And in this case, we use something called CLIF, which for our purposes right now is just a way of encoding formal logic in a Lisp-like syntax. And from that, it turns out we can actually pivot to any solver input that we want. This is the fundamental idea that motivates our architecture. And this is the idea we came up with in the article. So let's start with CLIF, the key point that allows us to connect these two disjoint worlds. CLIF, so it comes from something called common logic. It's a standard that grew out of some work done in Stanford in the 90s and then the early 2000s, and now it's a ISO standard that's in its second version. And it's a way of basically interchanging knowledge bases for computer communication. CLIF, in particular, is one of the concrete syntaxes of the standard, and it has a normative grammar. So that's why we chose it, because we have a standard grammar that we can implement ourselves and check against. And it's useful in particular for us because it subsumes the input languages of all the constraint solvers that has been used in the literature for these type of analysis techniques. And the conclusion, therefore, is just let's encode these semantics of the models in CLIF. And this way we can reason on using any solver we want with any kind of language. That's where we're going towards. And syntactically, if you're interested, it basically looks exactly like first order logic. All you got to do is use Lisp syntax, so a bunch of parentheses, and you put everything in prefix order. But otherwise, it has the same constructs as first order logic. So how exactly do we envision this happening? What is that semantic specification? In principle, what we're going to do is we're going to take a fragment of a model, and we're going to say, so this model, imagine we could have a much larger model, but here we're just exemplifying a single relationship. We're going to say for every element in this model, so in this graph, we're going to associate some translation rule. We're going to say this has to become this sentence in CLIF. And now what we do is we simply say, for example, the boxes, the features, they become variable declarations, sort of like declaring a sort if you're doing classical logic. So we're saying it's a Boolean, 1 or 0. And then we want to have this exclusion relationship. We want to specify that in a given configuration, we can't have both. And since we can't have both, the simplest way to encode that in a way that's numerical, and that there's a detail why we want to do this with arithmetic and not Boolean logic. We're going to say it's a sum. So it's a sum that's less than or equal to 1. So if either one is 1, the other one has to be 0 necessarily. But they can both be 0 and the constraint is still satisfied. Then our system takes, so the model, you can imagine it pushes it through the semantics, and out comes the semantics in Cliff. These are the concrete semantics for this model fragment. And then at the end, what we do is we take the Cliff, and we actually can spit out the representation in the constraint solver input language that we want. And you see it has the same shape and the same content. The only thing that changes fundamentally is the syntax. And this is what gave us the idea that we can unify all of these transformations under a single paradigm. So let's begin with a super simple example. Given this simple model, we want to find a given configuration. So how do we do it? Well, we envision the architecture with queries. So we're going to be declarative about it. We don't want to write code that tells us exactly how to interact with the solver. What we want to do is just give a query. We're going to say, I want to solve this model, I want to find a solution, and I want to do it with minizinc. What's going to happen is the system has to give us a valid solution. In this case, given the exclusion relationship, the only way we can have a valid solution is if we go towards the left. Now, let's go into a more complicated analysis of the very same model. We already saw that there's a problem with the exclusion on one side. Well, how about we formulate a more complicated query to understand why we can't select? Obviously, you guys can see it because it's a toy example, but imagine a model with tens of thousands of features and very long-range relationships. So once again, we're going to ask it to check satisfiability. We're going to tell it again that we want to use minizinc. And in this case, we're going to do something called an iteration specification. And it turns out many verification operations in software product lines are about iterating over the same constraint program and simply adding some verification constraints. In this case, we're going to take the variable associated with each feature and we're going to set it to 1. So in some way asking the question to the solver, if I want to include this feature, is there a solution? And if not, then we can conclude it's unsatisfiable and there's no solution, right? So the interesting thing is that many of the tasks require this kind of thing, but we don't want to program in hard code for a given language or for anything how exactly we want to do it. We want to give some query language that can allow us to express declaratively what we want. Here's an even more complicated example. Here's a dynamic system. It's not important what exactly it does. It models a system for flood prediction done in some previous work by one of my co-authors. And essentially what happens is we're simulating what would happen if the context changes. So on the right, you have these boxes that essentially encode the context of the system. And you're giving it the context, the variables. You're telling it, hey, right now the situation is this. What is the optimal solution? And what we do is we can associate arbitrary logical seems to, okay, sorry. So you can associate arbitrary logical formulas to your model. So it's hybrid. It's not just about the graph. And what we're doing here is we're defining the optimization target. And what we're saying is, given some optimization target, and the details are in the paper if you're interested, what we're going to say is the query is completely different. This time, we're going to use another solver, and we're going to ask for the optimal solution when we optimize for this objective value, which in this case is something about optimizing the satisfaction of all the requirements that are depicted here. So I hope the examples kind of illustrate what we wanted to do conceptually. Now let's get into the meat of the question and how exactly we envision the architecture to work. So you can read this diagram by splitting it down the middle. On the right side, you have the components, the 6 main components of what we envision this system, this kind of system would need to be able to function. So you have the main top component that contains everything else, that orchestrates the operation, that offers a web API. Underneath, you need to translate your variability model into Cliff. From CLIF, you need to translate it into a generic CSP representation, because even though the concepts, it's a subsumption, translating into the actual syntax has some caveats, and we talk about that in the paper of why we need this additional step. Then you construct the concrete constraint program from this generic representation, and then you use something called the solver controller, which we programmed, to basically do some meta programming and be able to control the solvers as if they were just a library. And finally, we write something called the bridge, which is the concrete, foreign interface with the different solvers, because generally they're not done in the same runtime. So you need to, it's a non-trivial problem to bring everything together under the same paradigm. And on the left, you have the data structures that are associated with the operation of this kind of system. So we set out and we designed this architecture before we even began to think about code, but we wanted to be able to cover everything we expected was necessary for this to work. And then we thought about the operation, right? And I just described more or less how the pipeline works. And so on the left, it's all about getting from your variability model into your solver input. And what you do is you pass through CLIF in the middle of the transformation. So you have this reasoning request that includes your model and your semantics, and together they get transformed into these different steps, and you can see every single step of the transformation. And we thought about this as a way of then feeding everything into the right side, which is all about controlling the solvers. So there's always this dual nature to what we're doing. First is transformation, and then we're going to control the solvers and do this meta-programming to be able to have this iterative solution with and parsing the query and understanding what we're demanding of our backend. And finally, we just get a response that we send back to the client, whatever he requested. And in this particular case, in the examples, we do some magic on the client to show it nicely with the little icons and so on. But fundamentally, this could be done from any client, since it's a web server. Then, after having posed the architecture, we said, okay, so let's do it. Let's make an actual implementation of this. And so the great thing is, all we had to do is instantiate the elements of the architecture. It turns out, in general, the architecture was easy enough to implement and create in a concrete manner, so that we could actually use the system and make a concrete prototype. So here, all you're seeing is that we actually added SWI Prolog, and we added Minizinc, and now we even have Z3 from Microsoft, but it's not on the diagram, it's just I'll show it in the demo. And we have the concrete data structures that we needed for the demo. So in this case, we are using some data structures related to the client to be able to do the initial prototype. But in theory, we can generalize this, and this is part of the future work we would like to do. Now we'd like to show you in practice what this means, because it's always nice to say something, but it's better to show, I'm sorry. So here's the very same example we already saw. And here we are in a web application made by some colleagues that is integrated with the backend I developed. And what we're going to do first is, well, let's look at the semantics. We want to get the semantics of our model. So we're going to go to this tab, and we're going to ask for the semantics. And so it's going to calculate all the CLIF semantics for our concrete model. It's going to give us essentially the set of equations that represent the relationships in our model. Then I have a couple queries prepared. So first of all, we're going to do satisfiability query. Are there solutions? And this time we're going to do it with Prolog. And Prolog says, yes, there are. There are solutions, no problem. Then we're going to go ahead and ask, can you solve the problem? Can you go ahead and give us a solution? And so we go to the result tab, and then we visualize the results, and now we get this result. Now we're seeing a concrete solution on top of the diagram. Let's reset the model, and let's do a final query. Let's do this iterative query to see where there are problems in the model. So let's do this again, and this time we're doing it with Z3. So we did it with SWI, then Minizinc, and then Z3. And this time, well, let's visualize again the results, and then you get the nice little one-way signs that I showed in the presentation. And all of this is being done dynamically. So if I go to the next tab, you have the actual server running, and for the dynamic part, you can even extract all of the code from Prolog or so on that you're interested in, and you can actually just take it out and we could export it as a file. And you could use that as a decision system for a dynamic software product line. So with that, I would like to just quite quickly conclude. So summing up the contributions, it's the first truly generic architecture for software product line engineering reasoning that is truly decoupled on the input and output side. We demonstrated the actual feasibility of using the pivot standard language, and we would like to motivate the community to actually, use it and follow our approach. And even if they don't use our actual prototype, they should try to follow the architecture, because we really give a lot of thought to how to correctly do this and decouple the two elements. And our implementation serves to demonstrate both the feasibility and the correctness of the architecture. In future work, we want to do more types of languages, and especially textual languages, which have a completely different set of challenges from the graphical ones, which are generally just graphs, directed graphs for the most part. Textual languages have a bunch of other challenges that are more difficult to integrate, because our current textual interface is simply adding cliff sentences on top of graphical models. We want to do incremental reasoning, and we're working on that at this time. We want to be able to add explanations and there's some previous work from other colleagues that have worked on finding explanations for the actual causes of the problems, and automated repair of the models is also another direction we want to check out. And obviously, like I just showed, the prototype works. It's out there. You can use it. The modeling client is currently on this address. It might change soon, so this will be valid for at least today. And our prototype of the actual implementation that I just showed you is on GitHub as well. Everything is public and open source, and you can have a look if you're interested. And I think with that, I thank you for your attention, and I'm happy to take any questions you might have.
Okay, I actually have two questions. One is, can you go back to the architecture slide? Like
of course.
What you show, I think it's the very first architecture. Oh yeah, it's this one actually, yes.
Yes.
So I noticed here you have JSON and then you have data type. Like, is JSON here just like a placeholder, means some serialized format, or you actually say, well, it's hard-baked, this is the serialization format you accept?
Well, this was an interesting question. We wanted to use, since Cliff is a bit of a stretch for most people, it's a weird and difficult thing to grasp at first, because it's not very well known today. We wanted to just take on the other side everything else we do as standard as possible. So JSON was just motivated in that terms. But in reality, you could use any serialization format. It's just easier for communication, and I guess it's the most well-known serialization format.
Right, but like JSON doesn't make encoding Cliff any easier than, say, protobuf, right?
No, but there's so in parts of you end up writing JSON yourself in several portions of like for example, when you want to write the queries, the query language is basically a JSON object with specific attributes, and then you write the query in this JSON structure. So many of the elements of the system work like that, and it's also tied to the modeling client, that everything in the communication has been done in JSON. But this is something that is not forced. You could use YAML, you could use anything you want.
I mean, sure. Like, so thank you for showing the query thing. But that is syntactical, right? Like, you can totally have a superficial language that translates some declarative into some JSON format. So you can totally just change this into, say, protobuf or like any other serialization format.
What we didn't want is to add additional DSLs on top of. We already said it's already asking the user to commit quite a bit to ask him to use Cliff. So we didn't want to ask him to do anything else weird. And part of the motivation for this, if I may, is so in product lines, almost everything is done in feature models. But the group I work in, they do a lot of DSLs for product lines. So the main motivation came out of a need from our group. And many of them don't understand, say, the solvers, or don't know how to code the backend and so on. So we don't want to give them anything that's too complicated to do. But all of these things can be changed, right? We try to do things as generic as possible. That is one kind of specific aspect. You're right.
Sure. So now, given that you have this JSON serialized format, right? I'm wondering what that data type is. So, like you have assumed some fixed serialization format. Then what is this data type for? Like, is that also some JSON serialized user-defined data type, or?
Well, so. Okay, so
like the reasoning task spec, like.
Yeah. So for the reasoning task, let me put it this way: the data types are abstract, if you will. They can be anything. And then the concrete one for the serialized communication is going to be in JSON, at least in this case. But in principle, the task specification is just some structure, some object, some data type that we're going to be manipulating. But it's not necessarily going to be typed to JSON. So
you are assuming there is a explicit or implicit transformation from this data type to JSON?
Not necessarily a transformation, but what you will necessarily have is, since it's a web client, a web API, you need some serialization format to communicate with the client. So basically what we're saying is that the reasoning request itself can be kind of any data type, but in concrete terms, for at least for a web server, we need some to specify some, and so we decided on JSON for this case.
Sure, so this any data type doesn't mean like any JSON object type. Is that kind of what you mean by it?
It would be basically any kind of object with fields, essentially.
Okay.
And anything that can be structured in this manner. I think there's a question.
Okay, thank you.
Thank you for the nice talk. I was wondering, you've shown 3 examples of SPL queries. Do you intend to grow these queries into a reusable library of SPL reasoning rules, queries, predicates?
Yeah, so that's why in the web client they have this saved query feature. What they want to do is that ultimately when the students develop their DSL and so on, they can save their queries as a sort of library. The difficulty with reuse in that sense is that many times the languages are quite different and the constructs might not be the same and the way you iterate over them are not the same. So sometimes you might iterate over the edges and not the elements. It's quite variable. So if in the example of the we didn't have time to get into it, but in the example of the dynamic system, there's a bunch of additional processing needed to be done on not just the edges, but some of the relationships are quite long range and difficult to parse. So there's a balance. But in principle, we would like users to be able to save all their queries and have a sort of like personal library. And on the application, there's like languages that are visible to everybody, so everybody could have access to the queries. And the idea is that obviously I have some prepared for you guys already. Of course.
So have you tried? So given this the textual modeling, right?
Yeah.
What do you expect ChatGPT to do? So suppose you can actually really describe this model in a textual format, and then you're phrasing your query in a declarative mode.
Yeah.
Basically some textual representation.
Yeah.
Do you expect ChatGPT will be able to give you a reasonably good response or?
The mic is the mic. Could you repeat the question, please? With the mic? No, the mic is off. The light should be green. Oh, it seems the battery is empty. Okay, perhaps you can repeat it?
Yeah, so if I understood correctly, the question is, what do I expect ChatGPT would do with these textual models? Honestly, I think I've done very little experimentation with product lines and ChatGPT. I do know that, for example, you can ask ChatGPT to draw a feature model, and it'll draw something kind of similar. And so you could give it like a description textually of, I have a feature model that contains this and that, and it'll give something more or less similar to an actual feature model. In terms of reasoning, though, on the model, I wouldn't expect ChatGPT to be able to do it. I guess it could maybe simulate in some, how it does it kind of gives you this confident answer of reasoning in some way, but I don't think it would do the same type of reasoning because I don't think it has a fundamental understanding of what's happening in terms of reasoning underneath. It's most, from at least what I understand of these kinds of models, it's all about predicting the most likely strings that continue from some prompt, but not necessarily reason as we would or as the solver would on what's happening underneath. And I don't know if there's enough of a corpus of Cliff as well for it to have trained on the manipulations of Cliff and what the outputs would look like. At least that would be my guess, but I wouldn't know for sure.
Sure, yeah, thank you. Yeah, then let's thank the speaker again.